Should the cache write to the database? Should it skip it? And when memory fills up, what gets thrown out? Today we find out. Welcome back. Part 2 of caching. Today, the strategies and policies. Quick refresh. In Part 1 we covered why caching exists, the hit versus miss model, and the cache hierarchy from browser to DB. Now let's talk about how to actually use a cache in your application code. Reads, writes, and what to throw out when memory fills. 3 questions to answer when you put a cache in your system. 1. When you read, where do you look first? 2. When you write, what do you update? 3. When the cache is full, what do you evict? Each question has multiple answers, and the right one depends on your workload. First read pattern, cache aside. This is the most common and the simplest to understand. When your app needs data, it asks the cache. If the cache has it, return it. Done. If the cache doesn't have it, the app goes to the database, fetches the data, stores it in the cache for next time, and returns it. The key thing is that the application is in charge. The cache is dumb. It just holds key value pairs. The app code handles the logic. Cache aside is what you write when you use Redis as a cache in front of your database. Flexible, transparent, easy to debug. Second read pattern, read through. Same idea, different responsibility. The cache itself is smarter. Your app asks the cache for the data. If the cache has it, done. If the cache doesn't have it, the cache itself goes to the database, fetches it, stores it, and returns it. The app doesn't know whether it was a hit or a miss. The cache hides the difference. Cleaner app code, but you need a cache that supports this. Not as common as cache aside. First write pattern, write through. Every write goes to the cache and the database at the same time. Both have to succeed before the write is considered done. The benefit is consistency. The cache always matches the database. No stale data. The cost is write latency. You're waiting for 2 systems instead of 1. Use write through for financial data, inventory counts. Anything where reading a stale value would cause real problems. Second write pattern, write back, also called write behind. When you write, you only hit the cache. The cache acknowledges immediately. Then, asynchronously, the cache flushes the change to the database. Could be every few seconds or every few thousand writes. The benefit is speed. Writes are blazingly fast. The cost is durability. If the cache crashes before flushing, you lose the writes sitting in the cache. Use write back for high write workloads where some data loss is acceptable. Analytics counters or activity logs. Third write pattern, write around. Writes skip the cache entirely. They go straight to the database. The cache only gets updated when something is read later. When do you want this? When the data you're writing is rarely read back soon. Logs, bulk imports, time series data you write a lot but query occasionally. No point filling the cache stuff nobody's going to ask for. Now the third question. The cache is full. What gets thrown out? Most common policy. LRU least recently used. Think of a stack of papers on your desk. When you touch one, it goes to the top. When you need space, you throw away the one at the bottom. LFU least frequently used. Different from LRU. You track how many times each entry has been accessed. The fewest accessed gets evicted. Better for stable workloads where popular items stay popular. FIFO first in, first out. The oldest entry exits, regardless of how often it was used. Simple but rarely the best choice. TTL time to live. Every entry has an expiration. 60 seconds. 5 minutes. An hour. When the timer is up, the entry is gone. Most production caches use LRU or TTL, often both at once. Quick recap. Reads. Cache aside is the workhorse. Read through hides the miss. Writes. Write through for consistency. Write back for speed. Write around for rarely read data. Eviction. LRU for most cases. TTL for time-sensitive data. LFU for stable popularity. Pick the combination that matches your read-write ratio and your tolerance for stale data. In Part 3, we tackle distributed caching. What happens when one cache server isn't enough? Consistent hashing. The thundering herd problem. The strategies for keeping a distributed cache fast and correct. Subscribe so you don't miss it.